We got that little microscopic conundrum behind us. So let's solve for P now. Solve for how does the polarization of this material depend on time, depend on frequency. So what I'm going to do is say P, which we had before. Before we had minus NE times this big thing that was R that included the electric field. So I'm going to pull the electric field out, and I'm going to put the minus NE back in. So the electric field we know that each atom feels is E local, the local electric field we just thought about. And the minus NE went inside of here, but there was already a little E there, so minus NE squared like that. And then over M omega squared minus J M gamma omega minus K. That term we've had, E to the minus J omega T. All right, now we know what E local was. P is, that was E naught plus, and then it was P over 3 epsilon naught, permittivity of free space. And now, to keep going without making a huge mess, I am going to write this as A over B. All right, so A equals minus NE squared, B equals M omega squared minus J M gamma omega minus K. It just makes the algebra a little easier in the next couple of steps, E to the minus J omega T. And then, no really, solve for P. That's what I'm supposed to be doing. Okay, let's actually solve for P now. So to solve for P, I would distribute that, and I would say we're definitely going to have E naught A over B e to the minus J omega T, and then this part I would bring over here. P over 3 epsilon naught A over B e to the minus J omega T. And I'd pull the P out and put it underneath. If we do all that, what are we going to end up with? We're going to end up with P equals something big in the top, E naught A over B e to the minus J omega T. So I'm going to put the A over B here, and the E naught e to the minus J omega T there. So that's the numerator. And then the bottom would have been 1 minus, and then it would be, let's see, 1 minus A over B, and then what's left is the 3 epsilon naught. So A over 3 epsilon naught B. And that's all that's left in the bottom. Yeah, so A over B over 1 minus A over 3 epsilon naught B, and then E naught e to the minus J omega T. And then we finally solve for P. Okay, but now we want to simplify it. All right, so let's keep going. P is polarization of the material, and the main simplification is to bring this B down. So it's going to be equal to A over B, and when you bring that B down, there's B there, and then that cancels that B, so B minus A over 3 epsilon naught minus A over 3 epsilon naught, and we still have E naught e to the minus J omega T. All right, now we're getting there. And now let's put A and B back in to really get P. So we saved ourselves some painful algebra, and A was minus NE squared over B. B was M omega squared minus J M gamma omega minus K. M over B minus A minus minus, so plus NE squared over 3 epsilon naught, and E naught e to the minus J omega T. So that's the answer. It doesn't look too intuitive yet, so let's mess with it just a little bit more. Let's divide the top by M, the mass of the electron, and divide the bottom by M, so that M goes away. This M goes away. Let's write the J a little bit closer. Move that plus over. It's K over M, and then 3 over 3 epsilon naught M. Okay. And then, let's see. Then you can kind of see it looks like a resonance, right? Because we're driving it at this frequency, and this is some real number under here. This is imaginary. But you can imagine when you drive it right at the frequency where omega squared equals whatever this is, then these two will cancel, and that's kind of like a resonance. When the denominator goes to 0, the response will get really big. But it'll be somewhat damped because we have an imaginary part there. So it looks a lot like a damped driven oscillator going through a resonance, which isn't that surprising because that's how we set it up. We have these electrons moving up and down, and we said they're kind of like a mass on a spring, and they have a little bit of damping, and they're being driven by an electric field. So really, you can kind of write this as a resonance by saying big P equals n e squared over m. That's related to their amplitude. And in the bottom, you can have, well, you could write an omega naught squared, a natural frequency squared, minus omega squared, plus the damping term, j gamma omega, times E naught, e to the minus j omega t, where you have a resonance or a damping frequency. Omega naught, the natural frequency of this resonance system, is what? It's a square root of k over m. That sounds familiar. Minus n e squared over 3m epsilon naught. Minus n e squared over 3m epsilon naught. That doesn't sound so familiar, but it's not surprising. This is more complicated than a mass on a spring. It has extra terms in it. So when we apply light to a dielectric, it'll make the electrons move up and down. It'll polarize the material. It'll make the polarization oscillate. And at just the right frequency, you can get a really big polarization. But it happens at all frequencies. You get a polarization at the dry frequency that you apply. Because this, you can see, is just the plane wave of the light that we applied to the dielectric. So now we're going to see what that does to the wave equation.